Okay, in the later part of the video, we discussed how the color of an indicator is going to change. Okay, when you put it in an acid or within the base. And in that first part, or in the latter part, we explain why the color change when the acid is in the burette and the base. Sorry, when the acid is in the conical flask and the base is in the burette, started from the burette. Why does the color change? Now we will just continue with when the base is rather in a conical flask. So we have our conical flask here with the base inside sodium hydroxide, and then the acid is in the conical flask. The acid is in the conical flask. Okay. So what happens is that if the acid is here, this is our HCl. We are adding HCl to sodium hydroxide. Now, why is it that when you drop the indicator here, the color is rather pink? Okay, but why is it that it is pink in an alkali solution? Now, the simple reason is that when you add this indicator, phenolphthalein, HIN, into this solution, what happens is that since the solution is made up of OH minus ions, phenolphthalein is going to dissociate. Okay, the forward reaction is going to be favored to form H plus plus IN minus. So this H plus of the phenolphthalein will be neutralized by OH minus. Alright, so the H plus there will react with the OH minus to form water, a water molecule. Okay, and you'll be left with what? IN minus. So more of this HIN will be dissociated to give H plus and IN minus, since there are a lot of OH minus ions in solutions here. Alright, so that this OH minus can now neutralize this H plus to give us water. So that is why this IN minus becomes very, very prominent in the base, okay, forming a pink solution, giving us a pink color. So this is why that is the reason why the color change in the acid is, as you saw in the other part of the video, was colorless, but in the sodium hydroxide is rather pink, or in the base is pink. Now, at any point, what is going to happen? The color changes from pink to colorless instead. Alright, when the acid was here, it gathered and the base was added, it changed from colorless to pink. And we explain why. Now let's see why it changes from pink to colorless. The only reason is that when this OH minus, when at any point, this H plus will be completely neutralized by OH minus. All the OH minus here are going to be consumed. So after the equivalent point, you will now an extra drop of H plus is going to be added. So that extra drop of H plus is going to now trigger, is now going to favor the backward reaction according to the Chatelet's principle. So when you put the extra drop of H plus, remember it's a weak acid, and of course these molecules here are not too many. And this one, the HCl which is added here is a strong acid. So you are going to have H plus combining back with IN minus to give us HIN. And so remember that this one is pink, okay, but this one is colorless. So when you add an extra excess of acid after the equivalent point, that excess of H plus will react with IN minus to form HIN. So the backward reaction is rather favored, okay, and the color will change from pink to colorless. Now let's look at the concept of buffers. What are buffers? What is a buffer solution? What is a buffer solution? Now, a buffer solution, a buffer solution is a solution which changes pH in accordance, or a buffer solution is a solution that resists changes in pH upon addition of small amounts of acids or bases. Okay, I'll take it again. A buffer solution is a solution which resists changes in pH upon addition of small amounts of acids or bases. Or in other cases, you can see another definition as a buffer solution is a solution whose pH is fairly constant upon addition of small amounts of acids or bases. Or is that it resists changes in pH? Its pH is going to, like in a certain case, it hardly changes. It resists the changes in pH. Now you have to put the word small acids or bases there, because you cannot tell me that you have 1 liter of buffer, you add 1 liter of acid there, and you still expect the pH to remain the same. So it's not going to be the same. Now, where do we have buffers? What are the applications? We have buffers in blood. All right, in our systems, we have buffers in blood which helps to buffer the pH of which helps to buffer to make sure that the pH of our blood remains constant. The pH of our blood is 7.35 to 7.45, and what helps to maintain it within that range are buffers. Okay, we have the bicarbonate buffer system in blood. We also have the amino acids, okay, which come from proteins, and we also have the phosphate buffer. Then we can also have buffers being applied in eye drops, okay, in drops that have to enter maybe the ocular part or the ears. Okay, we also have the application of buffers in agriculture, where they maintain the pH of the soil to make sure that it is neither acidic nor too basic for the plants to grow. So there's a particular pH for a particular soil and for a particular range of plants. Now, let's look at how many types of buffers are there. We have two types of buffers. There are acid buffers and there are basic buffers. Now, acid buffers are buffer solutions with pH less than 7. Okay, normally for an acid is pH less than 7. So acid buffers are buffers with pH less than 7. Okay, consisting of what? The solution of a weak acid, e.g., can have the solution of a weak acid, and the salt of that weak acid formed from a strong base. An example is CH3COH, that's ethanoic acid, and sodium ethanoate. So you see, the sodium ethanoate is formed from a combination of ethanoic acid and sodium hydrolysis, which is a strong base. So you say an acid buffer is a solution, is a buffer solution with pH less than 7. Formed from what? The solution of a weak acid and the salt of that weak acid formed from a strong base. While for a basic buffer, it is, or an alkali buffer or a basic buffer, it is a buffer solution with pH greater than 7. Okay, formed from the solution of a weak base and the salt of that weak base formed from a strong acid. For example, this is a salt of ammonia, which is ammonium chloride, and it's formed from the combination of ammonia with HCl. HCl is a strong acid. So I take it over pH, buffer solution with pH greater than 7, that's an alkali buffer, formed from the solution of a weak base and the salt of that weak base formed from a strong acid. So that is it, right? So I will use ethanoic acid in order to demonstrate what happens, or the ethanoic buffer to demonstrate what happens when you add an excess of acid into a buffer solution and when you add an excess of base into a buffer solution. Okay? Now when you add, let's consider the example of the acid buffer. When I add ethanoic acid in solution is going to partially dissociate. Remember, it's a weak acid to form CH3COO minus plus H plus. And we are going to have the salt CH3COO-Na dissociating to give us CH3COO minus plus Na plus. Please, for this one it is complete dissociation. Remember, it's a salt that has already been preformed, and this one is an acid, and there are other conditions which determine its breaking down. Now the last part is, remember, you have water. So water is H2O partially switching to give us H plus plus OH minus. Okay, so that is what we have, and all of these like that are found in one container. Remember, all of these like that, they are found in one container. So these are the three very, very important equations which happen with the buffer system. Now you can apply this for any buffer, but this is just an example, and it follows the same pattern for all of them. Okay, now when I add an excess of H plus ions into this solution, what is going to happen? Now remember that there is a large pool of base, right, which comes from what? There is a large pool of base which comes from sodium ethanoate, because it dissociates completely, but this one dissociates only partially. Remember, see, this one is a weak acid, and so only few molecules are going to dissociate. So this kind of ions, the ethanoic ions coming from the acid, are not as much as the ones which are coming from the salt. Now this is a large pool of base here, and so it's going to remove the excess of H. It's going to remove the excess of H plus from solution. Okay, it's going to remove the excess of H plus from solution to give us. So we are going to have CH3COO minus plus H plus. Okay, giving CH3COOH. So you see the backward reaction is stable according to the Chatelet's principle. Okay, so when you add excess of H plus, it means that the pH of the solution is going to be falling because the solution is becoming more acidic. So what happens is that this large pool of base here will combine with H plus to give us ethanoic acid, okay, thereby maintaining the pH of the solution at a constant value. Now let's look at when, okay, this is the equation. Please you take note of this equation. This is the equation for when an excess of acid is being added, okay. And now when an excess of base is being added, what's going to happen? Please remember, you see we had just one equation, then now when you add an excess of base, there are always two equations you are going to have, no matter the buffer you're using. So when I add an excess of OH minus, now is the case of adding an excess of OH minus, what is going to happen? Now this OH minus is coming in. Remember, this is a base. This one cannot combine with OH minus. So what can be able to help? Please, the sodium plus here is not. We are not using it. Okay, we are focused on sodium H plus and the OH minus or the ethanoic ion. So the OH minus will be removed. The excess OH minus will be removed by what? H plus in solution. Whether the H plus is coming from water or from ethanoic, from the solution of ethanoic acid, H plus is H plus. Okay, you cannot say one H plus. So any of the H plus there will combine with OH minus to give us water. Okay, combine to give us water. But what happens? You see that the amount of H plus which was found in solution is reducing because more of this H plus is rather combined with OH minus to give water. So it means that H plus is rather being removed from solution. So the amount of H plus in the buffer solution is falling. So what happens is that to compensate for that, according to the Chatelet's principle, more of ethanoic acid, okay, will dissociate. More of ethanoic acid is going to dissociate to give us CH3 COO minus plus H plus. So you will dissociate to replace back the H plus ions which have been removed from the solution by the OH minus to form water. So these are the two reactions which occur when a base or when an excess of OH minus is being added. And the first reaction that we saw was the reaction that occurs when an excess of H plus is being added. And I've explained why this one is 2. We are waiting how this one combines to give that. But that, for this case, when you remove excess of H plus, okay, the concentration of this one is going to, the concentration of H plus falls in solution, so the pH will rather be rising. So for us to replace back the amount of H plus in solution, we have to break, the ethanoic acid has to break down, okay, the forward reaction is going to be favored for it to replace back the H plus, okay. And that is that about buffer solutions. And I'll just, I think after this, I'll just have to give you the formula to calculate the pH of a buffer. Now, when you have been given the acid and the salt, the pH, I already told you the pH of the buffer solution is calculated using the Henderson-Hausbach equation. Henderson-Hausbach equation, which is written as pKa. We already saw what the pKa is. Most of the time, they give you the Ka of the acid. So you take negative log to the base 10 of the Ka to have the pKa plus log of concentration of the salt. Okay, log of concentration of the salt, which I will write as S, concentration of the salt over the concentration of the acid, which I write it as concentration of A. Now the acid there, in this case, can be ethanoic acid, and the salt will be sodium ethanoate. Okay, the salt is going to be sodium ethanoate. So please take note of that. All right. Now, in some other books, what happens is they write the pH as pH equal to pKa minus log of concentration of acid divided by concentration of the salt. Alright, so if you see minus, remember if you are putting minus, you should put acid over salt. But if you are having plus, it should be salt over the acid. Okay, and that is all for the calculation of the pH of a buffer solution. Now we are going to quickly talk on we'll simply talk quickly on salt hydrolysis, and that is the last thing we are going to be doing for this topic, and that will be the end of the topic. Alright, that will be the end of the topic. So we talk about salt hydrolysis. Now, what is salt hydrolysis? Salt hydrolysis simply explains how a compound can react with water. A compound is being hydrolyzed by water, and the OH ions of the water remains intact. Okay, so salt hydrolysis is a phenomenon where a substance reacts with water and the OH minus ions of water remain intact. Okay, that's the definition of salt hydrolysis. Now, what is it very, very important for us to study salt hydrolysis? It is because some solutions can be acidic, some salts can be acidic, or some of them can be basic. For example, in some questions in the GC, they ask you to calculate, to tell us why a solution of sodium chloride is neutral, or why a solution of magnesium chloride has a pH of 7, or is just neutral, and why is it that of aluminium is rather acidic. Okay, a solution of maybe aluminium chloride is acidic, or why is it that a solution of ethanoic acid is going to be basic, okay, or alkaline. So we are going to see all of that. I've already defined salt hydrolysis. Now let's look at what is going to happen. Now, for example, when you have cations, okay, when you have cations with small size and very high charge density, okay, cations that have small size and high charge density. Cations with small size and high charge density. What happens? For example, if you have aluminium, okay, remember in water, aluminium is going to form a complex ion, all right, in water. When you have aluminium ions in water, they form a complex ion, so you're going to have hexaqua, aluminium, hexaqua, so 6 water molecules surround the aluminium molecule to the power, okay, 3 plus, it has a charge of 3 plus, okay. Now, what happens is that aluminium, remember aluminium is aluminium 3 plus, so it has, if you look at the size of aluminium is very, the size of the aluminium ion is small, and of course its charge is plus 3, so it has a very high charge density. So this high charge density, since it has a high charge density, it can be able to polarize the bond of the water molecule. Remember, you can write the bond of the water molecule like this, okay, HOH. So you polarize the water molecule to break this bond to form H plus and OH minus. Now remember, I said for salt hydrolysis, the species reacts with water and the OH ions remain intact. So once that aluminium 3 plus does that to polarizes the water molecule, we are going to obtain aluminium. Now, since it polarizes the water molecule, we are going to have 5 water molecules, okay, and an OH minus ion. So it's going to remain intact and the charge now becomes 2 plus. Now the oxidation state of aluminium is 2 plus 3, alright, because here you have X, water is 0, alright, times 5 is still 0, but minus 1 for OH minus, that's the oxidation state, equal to plus 2. So when this negative 1 goes this way, it still becomes plus 3. Now plus H3O plus, okay, you see it's balanced in terms of charge. The charge that way is plus 3, this one is also plus 3. So you see, he has polarized the water molecule to produce what? H plus and OH minus. Now the OH minus remains intact, while the H plus will combine with a water molecule to form the oxonium ion. And please note that oxonium ion, concentration of oxonium ion in solution is the same as the concentration of H plus, because it is typically H plus, because H plus simply goes into solution and binds with the water molecule. So telling us that oxonium ion is like H plus ions in solution. Okay, so please, you are going to have here, you have this aluminium. Of course, you have seen how you break down your plus, H3O plus, if you can't see from that other end. So you have H3O plus, okay, and this H3O plus here, as I said, the concentration of OH3O plus oxonium ion in solution is the same as that of H plus. Okay, that is it. So we see, as I said, cations with small size and very high charge density, all right, are going to form solutions that are acidic. All right, are going to form acidic solutions. Cations with small size and high charge density, in this case is aluminium. So they will always ask, why is that a solution of aluminium chloride is acidic? Okay, this is the reason, because aluminium has a very small size and high charge density, which enables it to polarize the water molecule, okay, to produce H plus and OH. The OH remains intact while the H plus is being released in solution to form an acidic solution. Now let's look at the other part. Now this scenario is also the same, alright, it's also the same for most compounds of transition metals, most transition metal compounds, alright, or most sorts of transition metals, their solutions are also acidic. Why is it so? Because the D electrons of the D subshell, Alright, please take note. The electrons of the D subshell do not have shielding effect on the nucleus. So they don't have any shielding effect on the nucleus. And so if they don't have any shielding effect, what happens is that the charge of the nucleus will be high enough, since it's not being shielded, to polarize the water molecules to produce an acidic solution. So that is it. Okay. And the next part that I'm going to talk to you about. So I've already talked to you about aluminum, and then I talked to you about transition metal compounds. Why their solutions are usually acidic is because the D electrons do not have any shielding effect on the nucleus, so they produce cations with very high charge density that can polarize the water molecule. Okay. Now the next part is of course anions. That was cations. So anions, which are conjugate bases of acids, okay, are going to produce an alkali solution. What do I mean by that? Now, if I take a solution of COO, sodium ethanoate, okay, a sodium ethanoate salt. Now, sodium ethanoate will dissolve in water to give me CH3, COO minus plus, sodium plus. Alright? Remember, this one is a conjugate base of an acid. This is a conjugate base of an acid. Alright? So that conjugate base of an acid, remember, it is in water. Okay, it is in water. So it reacts with water. Remember, water is amphiprotic, so it can act both as a proton donor and as a proton acceptor. So CH3CO minus plus H2O, alright, will combine to give us CH3COOH. So water donates an H plus to H and forms OH minus. And so this OH minus in solution makes the solution to become basic. So salts, solutions or anions which are conjugate bases of acids or of weak acids are going to form alkaline solutions. So this is it about salt hydrolysis, because we have seen the salt like aluminum chloride, we have seen what is going to happen, and we have also seen for sodium ethanoate is an example. Okay. Now the very last thing I'm going to do is just to give you what is going to happen for the different combinations: strong acid, strong base. How is their solution? So if they were to ask why is it that sodium chloride solution is going to be neutral, the reason is because sodium plus ions do not have enough high charge. Their high charge density is not too high enough to be able to polarize the water molecule to produce H plus ions in solution. That is why it remains neutral. It's neither acidic nor basic. Okay. So what happens is that when you have a strong acid and a strong acid, for example, HCl. Please take note. I won't write too much on this part. You take note. So when H plus, so when HCl, for example, strong acid, strong base. When strong acid, strong base combine, the kind of salt they can form can be sodium chloride. Okay, and the solution of this salt is what? Neutral. Right? This kind of salt can be neutral. Okay, no charge, enough charge density for it to be able to polarize the water molecule. Okay, you can have if you have a strong acid, say HCl, and weak base, ammonia, you're going to have something like ammonium chloride. Okay, this solution is going to be acidic. This solution is going to be acidic because when this one breaks down, it will release H plus into solution. Okay, if you try to write down the equation, you see the solution will be acidic. Now, if you have a strong or a weak acid, which is CH3COOH slash a weak acid, strong base here, for example, can be sodium hydroxide. I can have a salt like sodium ethanoate, CH3COONA. Alright, this salt, of course, we have already seen that is going to be basic. Solution. And then the last part is when you have a weak acid, for example, CH3COOH slash weak base, ammonia. You're going to have something like ammonium ethanoate, NH4. Alright, this is the salt you're going to have, ammonium ethanoate, and this solution will be almost neutral. Okay, their own salts are always very extra, almost neutral. Alright, so so far we have 4 lectures on this topic. Each of them I think is close to sometimes 30 minutes or above. Please, you make sure you follow all the 4 videos and you follow all of what we have discussed. Now, all is left for you is just to answer questions. I've answered every single thing you are supposed to know about the topic I have told you, and I think here we're going to conclude with the topic. So see you in the other videos. God bless you. Thank you very much.